Hey, good afternoon. So today let's finish lab 4, so the last one. Yay. Um, so for lab 3, we did lots of testing on proportions, like two-sample proportion test, chi-square test, right? So today we're gonna do some more things, but we're gonna continue with means, okay? So we're gonna do one sample mean test, two sample mean test, pair sample test. All of these topics will be mentioned during the class today. So for this lab, the story behind the data is called speed limits and traffic fatalities. So basically, in 1995, the US federal government signed a bill called the National Highway System Designation Act, which allows each individual state to change the speed limit from 55 to, I guess, whatever they want. So in 1996, out of the 50 states plus DC, so we have 51 districts, let's say, 32 of them decide to increase speed limits, which means the other 19 did not change, okay? And the purpose of the study is to compare the change in traffic fatalities in the states between the states that held the limit and the state that increased the limit. So the data here collected are the numbers of traffic fatalities on interstates in 95 and 96 for each of the 51 districts. So as you can see, 95 is before they passed the bill, 96 is after they passed the bill. Okay. The data, you can find the data from the website here. So for the data we have, as you can see from the right side, again, I randomly selected 41 districts, so the pattern in my data will be slightly different than yours, okay? So for each state, so we have the named state, we have increase is a binary variable, so either no or yes. The FAT 96, it's the number of interstate traffic fatalities in 1995. FAT 96, it's the 96 fatality data. The percent change is computed using the change in number of basically 99 minus 95 divided by the fatalities in 95, so and times 100. So if it's a positive number, it means the fatalities increased. If it's a negative, it means it's decreased. So for example, for Alaska did not increase the speed limit, and the number of traffic fatalities decreased from 31 to 22. On the other hand, you can see for Kentucky, they also did not increase the speed limit, and the number of fatalities is roughly similar, increased 3. And for example, for Washington, the state of Washington, they increased the speed limit, and the number of traffic fatalities increased from 67 to 90, and that's a 34% change. Okay. So first, let's comment on the design. So in particular, whether we have observational study or experimental study. So again, whether we have experimental or randomized study depends on whether we have any manipulation on the treatment. Here, the treatment is what? It's the decision whether the state decided to increase or not. So, for example, if I am, for example, the president, or no, the secretary of the transport department, let's say, and I want to do a little bit of experiments. So what I do is I randomly assign each of the state whether they're going to increase or not, and then I'm going to compare the numbers to see whether increasing the speed limit will increase the fatality or decrease fatality. But if you want to do an experimental design, the key thing here, you have to randomize the decision. Randomize the decision whether the state is going to increase or not, which is not the case in practice, because in order for the state to pass a law, they're not some of your experimental unit. They have to, the state itself make the decision. It's not like there's some unseen hand who is, manipulating all of this. So apparently this is just observational because we have no control over which state is going to increase or not. Okay. So if it's observational study, then the inference or interpretation we can make can only be correlational or associational. For example, if we do find out that the states that increase the speed limit also they have a higher fatality, you couldn't say this is caused by the decision they're making, because there's maybe a thousand different things that's happening simultaneously. Like, what's the behind the reason that they want to increase the limit? And also, there are a lot of factors that can come to the equation. And since we don't have randomization, the random assignment, we cannot conclude that the changes that happened is caused by the increase on the traffic limit or not. Okay. So no causal link because it's an observational study. Okay. Okay, let's look at question 2. Question 2 asks you to display the difference for the percentage change between the states that increase. So we have two groups, increase versus no increase. Okay. So first it asks you to do a box plot. So box plot, graph, chart builder, no, not chart, that's PSS. Graph, box plot, and then the percentage of change, fence of outliers, and then let's do this. Oh, side by side, let's go back. Sorry, we're going to group by increase or not. We want them separately. Okay. Let's do 1 row, 2 columns. So we have 2 plots side by side. Okay. So as you can see from the box plot, both of them are quite symmetric. The no group have 2 outlier, row 11, New Jersey. New Jersey it's because they have such a high increase, 44%. Another one is oh, it's so hard to. Okay, what's the other one? Jesus. Okay, it doesn't really work. Clear. Row 11, row 17. Okay. Wisconsin. Wisconsin also have a very high percentage of increase, so 41%. Okay. But otherwise, both distributions are quite symmetric, I would say. And then it asks you to comment on the center, and the spread, and then the shape and outlier. So for the center, we can see for the no group, so no increase group, the medium is negative. Negative means decreased, so that's a good thing. For the yes group, the medium is positive, which means increased. So as you can see, at the medium level, the yes group has a higher fatality percentage change over the no group. Okay. And then for the spread, this group also have a larger spread. The IQR is larger. For the shape, I just commented, and there's 2 outlier here. Okay, that's 2. Very easy. So 3, instead of graphical summary, we're going to do numerical summary. So we're going to do the mean standard deviation for the percent change for the true group. So we are still looking at the variable percentage of change. So let's do statistics, summary statistics, columns, percentage of change, group by increase, and then let's do n, mean, and then standard deviation. Is that all they asked? Mean and the standard deviation. Okay. So for the mean level, we can see the mean level yes group is higher, standard deviation is higher for the no group. Okay. 4. See, when here they ask you to compare, you can just compare the numbers. You don't have to do any testing. It's just compare the raw number, which one is bigger, and that's it. So for 4, it says before comparing the two groups, let's take a look at this group separately. So here you will use the confidence interval for the person. So use the sample tool to obtain 95% CI for the mean percentage change in fatality from 95 to 96 phase output, which interval is wider. For each group, I guess each group here means yes or no group. Okay, so confidence interval. So test, since here we're doing t statistics y, because one reason. First reason, we don't know whether the population is normal or not. Second reason, we don't know the population sigma, so we have to use the sample standard deviation S to replace sigma. So we fall into the t-statistic, the small sample category. And we're doing one sample with data. And then we're doing 95. No, we're doing percentage of change, group by increase or not. We're doing hypothesis test confidence interval for 95%. And then let's do this interval plot. It might be interesting. So the first output gives me the confidence interval. So for example, for the no group, I have a confidence interval from -23 to 6, which includes 0. Okay, so here it asks which one is wider. So the first interval has about 29, the length. The second one is 19, so the no group has a wider interval. So y is wider. So again, remember, how do we measure the length of an interval? So the confidence interval is the estimate plus minus critical value times SE, which means the length of the interval, which is the upper bound minus lower bound, equals to 2 times critical value times SE. So if you have a larger SE, then the interval will be wider. So as you can see, the standard error for the no group is larger than the yes group, so that's why the interval is wider. Do we have any overlap? We do. From 4.8 to 6.6, there's a tiny bit of overlap, not a lot, but a little bit. So a little bit overlap might mean that there might be a chance that this two quantity might be the same. So the two group, yes versus no, might have the same mean of percentage of change. Okay. Here you might be asking, isn't percentage change a proportion? Why we're not using proportion test? Again, remember, for proportion test, we only have one p-hat. We have two categories, yes or no, and we have one proportion to compare. Like you compare, for example, you can compare the average proportion to 0 or not. Which is not the case here, because remember, when we are doing the confidence interval for proportion, what information do we need? We need sample size n, and we need p hat, and that's it. But in this case, we have the percentage change for every single state. Okay, so that's different. Let's see 4b. Because when you remember, when we're doing proportion test, the input here is a binary, like yes or no, right? But here we have actual numbers. So like for example, I can do a proportion test on increase to test whether it's 50%. So I'm testing whether the proportion of the states that increase the limit equals to 50 or not. That's proportion test. But here this is mean test. Okay, even though the number, the quantity here is a proportion. Okay, think about it. 4b asks, based on the interval, does it appear the traffic fatalities increase for those? What about those who retained? So for the states, for the no state, so n here means the states that retained the speed limit. The interval is mostly negative. There's a little bit positive, but mostly negative. Mostly negative means mostly it decreased. Okay. For the yes group, it's all positive. All positive means almost all the states that has increased the speed limit has a higher chance of have a larger have more fatalities. Okay. Let's take a look at the interval. Oh, the interval plot, just visualize it. See? The visual, if you visualize the no group, the majority is negative, a little bit of positive. If you visualize the yes group, the whole interval is positive. Oh, you don't have to paste the plot. This is just help you visualize the interval. Okay. Let's take a look at 5. Oh, and that's it. This one is really short. Good for you. 5 asks you to use 2 sample tools to compare the average change of limit between the states that increased and that did not increase. Use the SAM methods that do not poll the variance. In class, we'll talk about the 2 options. You can poll the variance and do not or not poll the variance. And we have a rule, a way to make this decision. Here, it specifically asks you to do not poll. Okay, so we're doing hypothesis testing. So the question here is there significant evidence that the average percentage change in traffic fatality was greater? So keyword is greater, one-side test. Greater for the test states that increased, whether those retained. Okay, so let's do T statistics to sample with data. Okay, so for the first sample, let's say for those increase, let's say increase group. So percentage of change where the increase equals to, again, in the data we used no and yes, right? Equals to yes. So the first group is increase equals to yes. That's the yes group. Okay. The second group is also percentage, but we are using percentage equals to, oh no, that's so wrong. No, increase equals to no. Okay. And then we are testing whether the alternative is whether it increased. So increase was greater. So greater, larger than. And that's it. Let's do compute. So this is the results. Okay. So let's answer the question. So the null and the alternative is here. You should also remember paste the mu1, mu2, because if you don't define mu1, mu2, I have no idea what's your mu1 and what's your mu2. Okay. The distribution of the test statistics is a t distribution with degree of freedom of 27.64. This degree of freedom might be a little bit. Okay, let's go back one more thing. Poll variance or not. The default is do not poll, which is what the question is asking. So that's good. So it's a t distribution because we're doing a t statistics. This degree of freedom formula is slightly different than the ones we use in formula sheets. This one is more accurate, but it's more difficult to calculate. So the one we use in the formula sheet is kind of like an approximation for this, okay? So it's a t distribution with a degree of freedom of 27.64. The test statistics is t statistics 2.67. The p-value is 0.006. So if you're using 5% as the confidence level, sorry, the confidence level, because p-value is small, so we are rejecting. Rejecting means that we have enough evidence to say that the state that increased the speed limit has a greater number of traffic fatalities. Okay, so what the assumption? So the assumption we have the assumption for so first, simple random sample. Second, the two distribution, both distributions have to roughly follow a normal distribution, and the third, these two sample has to be independent. For the normal assumption, central limit theorem. Central limit theorem says 30, right? I don't think here we have 30. We have close to 30. But if we go back, let's include this box plot and histogram and QQ plot. No. And let's do this QQ plot. It didn't ask for QQ plot, okay? It asked for the box plot. For the box plot in question one, we see they're quite normal. So they're quite symmetric. And symmetric distributions are usually pretty normal, okay? But let's do it one more time. Box plot. And let's do this QQ plot. So next, so from the box plot you can see it's quite symmetric, so I would say they are pretty good. For the QQ plot, as you can see, if again for the QQ, how to see the QQ plot? The red line is the reference line, so if every single point here is one state, if your data follows a normal distribution, the points will be close to the line. Like in this case, they're pretty close. I mean, they're not exactly on the line, but the difference is pretty random and pretty small. So I would say the yes group is quite normal. That's good. Similarly, the no group seems to have a little bit of pattern, so it's definitely worse than the yes group, but it's not super bad. So I would say, okay. Let's B. C asks you to report the confidence interval for the difference. So for the confidence interval, let's redo, or let's do it again. Let's redo that. No. The results. Let's go back. Instead of doing hypothesis testing, let's do confidence interval with 95%. Okay. Let's do compute. So the confidence interval is from 5.25% to 39%. So as you can see, the whole interval is positive. Which is positive? Mu1 minus mu2 is positive. Mu1 is what? Yes. So yes minus no is positive, means yes is bigger than no, means yes group have a greater number of traffic fatalities, which is consistent with hypothesis testing. So the whole interval is above 0. Okay? That is everything. Okay, great. Okay, have fun. Bye.